So here we're going to talk about how to name coordination compounds. So nomenclature, there is a regular procedure for naming these coordination compounds. It is similar to the IUPAC way of naming organic compounds. And there's also some similarities with ionic compounds as well that we'll see. There are unfortunately still many frequently used common names for many of these compounds, which can make it a little confusing. But we're going to focus on the kind of the procedural naming methods. Yeah, and again, unfortunately, just like organic chemistry, the naming rules are not always completely adhered to. A lot of these are just for historical reasons. We really just want to expose you to the rules so you can understand and create complex formulas from the names and things like that, not necessarily always perfectly being able to name everything. So when you do see these coordination compounds in a lab manual or in a text, you can get the chemical formulas and eventually the structure. So for monodentate ligands, anionic ligands take an O suffix to the root name. So like hydride becomes hydrido, fluoro, chloro, bromo, iodo, so on and so forth. Even like for oxygen, oxido is the IUPAC name, but oxo is very common, for example. Same thing with isothiocyanate. It's technically thiocyanado N, which is indicating that it's N bonded versus S bonded. So there's kind of some unfortunate ones like that. And then there are some common name ones. So the three common ligands take special names: aqua, carbonyl, and amine. It should be noted that this amine is with two M's, which again is kind of unfortunate terminology because I think that this can lead to some confusion as opposed to an amine functional group in organic chemistry. There are other chelating compounds. A lot of them are amines, so nitrogen being a very common Lewis base in terms of coordination chemistry. So, for example, a bidentate ligand, ethylene diamine, also abbreviated EN, ENE. And you can write out either that formula or that abbreviation. It is common in writing coordination compounds to actually just write the abbreviation in the chemical formula, especially for really common ones like EDTA, ene, diene, triene, and things like that. Here are a few more. So instead of acetylacetinato, you can just say ACAC, ACAC, as the abbreviation. So that's a bidentate ligand that, again, is fairly common. And you can see that the common name is different than the IUPAC name once again. Instead of 2,4-pentane dione, which, diono is what it ends up being, it's just ACAC. Same with BIPI and some things like that. And oxalato just is OX for oxalate. And there are some interesting, maybe now would be the time to mention it, but you can see for oxalato, it kind of has two different bidentate ligands on the same molecule. So this can actually cause some interesting bridging between different metal centers. Here's some more. So DPPE. All right, so in terms of the actual rules, the positive ion is named first, followed by the negative ion. So this is very similar to simple inorganic compounds like sodium chloride. And so this will matter in terms of whether the complex ion is the cation or the anion. You're still always going to name the cation first. So here's an example of that. Here we have a complex ion that is positively charged, +1 charge. So you would name that complex ion. In this case, the complex ion is diamine silver 1. And then you would name the anion, the negative ion, chloride. So the inner coordination sphere is enclosed in the square brackets, remember? And then within that square bracket, the metal is, in the formula, the metal is written first. So in naming, the ligands are named before the metal. The metal will be at the tail end, and then you have some indication as to the charge of either the metal or the charge of the complex ion. And we'll talk about what that means in a second. So again, here it is. So tetraamine, copper 2 sulfate. So when we have identical ligands, that's given by a prefix. So in the ligand names include, if the ligand name actually has prefixes or is fairly complicated, it is set off in parentheses and the second set of prefixes is used. So a simple prefix would be like dichloro, tribromo, some things like that. But bis, tris, tetrachus, those are complex prefixes that mean the same thing in terms of 2, 3, 4. But that would be used for something like diene is a complex molecule. So you would end up using, if you had 2 of those, you would use the complex prefix. So that would be bis. So here would be an example. So for ethylene diamine, you can see that that is fairly complex. That is ene, recall. So ethylene diamine, it already has di in it. So if you want to indicate that there's 2 of them, you would say bis, and then within parentheses, ethylene diamine. So chloro is not complex, that's simple. So it's just dichloro. But then when you want to indicate that there are 2 enes, so you would say bis, and then in parentheses, ethylene diamine, cobalt 3 in this case. We're going to have the ligands named in alphabetical order according to the name of the ligand. So this excludes the prefix. And again, exceptions are pretty common, so take that for what you will. So here we have tetraamine dichlorocobalt 3. So the tetraamine, amine is an A that comes before C for chloro. So you should say tetraamine dichloro as opposed to dichlorotetraamine. And then cobalt 3. Anionic ligands are given by the O suffix. Neutral ligands retain their usual name, and then recall that there were these special scenarios, so aqua, amine, and carbonyl. So hexaamine, cobalt 3 chloride. Again, just like with naming inorganic salts, you didn't need to say for the counter ions, you don't need to indicate how many there are. So you didn't need to say trichloro at the very end. That is indicated by the charge of the complex. So the complex ion ends up having a +3 charge because the cobalt is indicated to be an oxidation state of +3. The amines are neutral ligands. So that means that whole complex ion is +3 charge associated with it. Therefore, we know that there are 3 -1 counter ions here for the chlorides. So we know that there are 3 chlorides there. So that's an important note in terms of naming. There are actually 2 systems for indicating the charge or oxidation number of the complex ion and that metal. If the charge is negative, the suffix 8 is added to the name of the coordination sphere. So that would be at the very end of the metal's name. And then there's 2 different systems. We have the stock system, which puts the oxidation state of the metal as a Roman numeral in the parentheses after the name of the metal. So this is what we've been seeing so far. And this is, again, similar to naming ionic compounds. If the oxidation state of that metal, if there are multiple different oxidation states that metal can have, we need to indicate the oxidation state of that metal. Again, it's not telling you how many metals are there or that sort of thing for ionic compounds. It is telling you the oxidation state of that metal. And so that's the same is true here for the stock system. There is an alternative system, and that's the Ewing-Bassett system, chemical abstract system, which puts the charge on the coordination sphere in parentheses after the name of the metal. There are some nice advantages to this because this helps indicate whether the charge of that complex ion is positive or negative. So it's really clear whether you need the ATE suffix at the very end or not. Where sometimes in the stock system you have to do a little bit of simple math to figure out whether your complex ion is cationic or anionic. So here would be an example of an anionic complex ion. So we would say tetrachloroplatinate 2. So platinum has a +2 oxidation state, so that's where the Roman numerals 2 would come in. Or you could use the other system, the Ewing-Bassett system, and say tetrachloroplatinate 2-. And so that's, if it's not Roman numerals, you're indicating the actual charge on that platinum complex. And you could backtrack and figure out that the oxidation state of platinum is +2 here. But it's nice because since it's showing you very explicitly that that complex ion is a -2 charge, therefore you would know that you can't just say platinum, you'd have to say platinate with that ATE suffix at the very end. So there's some advantages and disadvantages to both of these systems, and you'll need to know how to use both of them, and you'll see both of them. So isomers are also indicated by the appropriate prefix, for example, cis or trans, and then fac or mer, which is facial or meridional, and you'll see what that is later. Bridging ligands take on the prefix mu, so that's just indicating that it is a bridging ligand in that system. So you could talk about mu amido, mu hydroxo bis tetraamine cobalt 4+. So that is showing that the hydroxo is bridging and the amido is also bridging. So those would be examples of bridging ligands in these systems. So this would be if you have multiple metal centers. So it gets a little bit more complex, and it gets pretty complex pretty quickly. But at least now you have some understanding what that mu would mean if you see that in a name. When a complex is negatively charged, the names for the following metals are derived from the sources of their symbols, not their English names. So it comes from those Latin roots. So there's things like cuprate, ferrate, argentate, plumate, stanate, aurate. So it's those that you would need to know. I think you're familiar enough with cuprate and all of that. So these are kind of some of those special situations. So again, here we have two anionic systems, tetrachloroferrate 3. Again, you could also call that tetrachloroferrate -1. And here's dicyanoaurate 1. All right, so let's try some of these. Let's name the following coordination complexes. You could pause it here, and I'll pull them up here in a second. All right, so hopefully you paused and tried those out. So this first one, triamine trichlorochromium 3. It should be kind of noted if it's neutrally charged coordination compound, we really don't write 0 for the charge. You really would end up using that first stock system in general, so indicating the oxidation state of chromium to be chromium +3 in this situation. Again, you can just figure out that chromium is +3 in this situation because you have 3 chlorines there. You know that each of those are -1, and the amine groups are neutral. So in order for that to charge balance, chromium is a +3 oxidation state. All right. Here we have dichloro ethylene diamine, platinum 2. So you don't need platinate, it's not negatively charged. You just keep it as platinum. And ethylene diamine, there's only one of them, so you didn't need to do bis or tris or anything like that, and you did not need to put that in parentheses. And ethylene diamine, E comes after C, so you should start with dichloro. All right, here we have bisoxalate, platinate 2, or you could say platinate 2 minus with the other system, indicating that it has a -2 charge associated with it. The oxidation state of platinum is +2, so oxalate is -2 charge associated with it. And oxalate is complex, so you wouldn't just say dioxalate, you'd say bisoxalate and put oxalate in parentheses in that situation. All right, here we have pentaaqua, bromochromium 3, or again, 2+. So we figured out chromium has a +3 oxidation state since the whole complex is +2, and a bromine is -1. The waters are neutrally charged, so we could figure out that chromium has a +3 oxidation state there. And again, the whole complex ion is positively charged, so we do not need chromate, it's chromium 3. Yep, there's pentaaqua, and aqua comes before bromo. All right, here's the last two. We have tetrachloroethylene diamine cuprate 2, or 2 minus. Again, it's negatively charged, so we need cuprate instead of copper. Tetrachloro is going to come before the ethylene diamine. And you can see here, ethylene diamine is written all the way out as opposed to just writing EN, which you saw on letter B. So either is totally fine. Oftentimes you're going to see the abbreviated version like EN. And then here's that last one. We have tetrahydroxoferrate 3 or ferrate 1 minus. All right, so those, let's try kind of going the other direction and writing out what these would look like from the name. So give the structure of the following coordination complexes. So you could just write out the formula or actually write out the entire structure. So this is tris acetyl acetinato iron 3. The acetyl acetinato, remember, was ACAC. That was ACAC. And again, that's a fairly common ligand, so either would be totally appropriate. So again, you can pause this and we'll go through these in a second. Try give all these a try here. All right, let's draw this first one. Actually, showing the structure here is nice because there's only three. There's three of these ACAC ligands, and each of those ACAC ligands are -1 charge associated with them. So it actually is a neutral complex, but each of them are bidentate, so you still get an octahedral coordinated complex here with those 6 oxygens, even though there are 3 ligands, and then iron is in the center. So there is no charge associated with this entire complex, even though iron has a +3 oxidation state. All right, hexabromoplatinate 2 minus. So this is, again, octahedral complex. There are 6 bromines. The whole complex is 2 minus, so it's platinate. And therefore, we would have a +4 oxidation state on the platinum. All right, here we have potassium diamine tetrabromocobaltate 3. So potassium is the counter ion, so and there would just be one of them in this situation, since we can figure out that the complex ion is anionic and has a -1 charge associated with it. If cobalt has a +3 charge and you have 4 bromines, that has a net of -1. But if you're just drawing the coordination complexes, you can ignore that potassium for now. And this does actually have two different isomers. There is a cis and a trans. You didn't necessarily need to draw both, but know that they could be distinct and actually have different properties associated with them. They're different isomers. All right, so tris ethylene diamine, copper 2 sulfate. So again, we have sulfate as the anion, so that's labeled second. So we would have one sulfate here for every one tris ethylene diamine, copper 2. And you can see that we're now using this little shorthand. So you could draw in the entire structure, or sometimes people get lazy, or actually just for clarity, instead of drawing that entire complex, you're just drawing the local environment around the copper, indicating that there are nitrogens there, and then just kind of showing that there is some bridge between those, showing that there's just 3 of them, but it still is, since they are bidentate, it still is octahedrally coordinated. Hexacarbonyl manganese 1 perchlorate. So again, we have perchlorate, but the cationic complex ion is hexacarbonyl. So hexacarbonyl is seen there. Manganese 1, carbonyls are neutral, so manganese 1 means that whole complex will have a +1 charge associated with it. Ammonium tetrachlororuthenate 1-. So the 1- tells you that whole complex ion has a -1 charge, so there'd be 1 ammonium as a counter ion there. And again, the cation is labeled first, so here we would say ammonium and then say the complex ion. Tetrachloro, so 4 chlorines, ruthenate. So the whole thing is -1 charge, so the ruthenium would have a +3 oxidation state. All right, so that was nomenclature. We'll move on to, we've shown a few isomers, but we'll talk more explicitly about some of these structural isomers and hard, soft, acid, base theory, which can help justify or determine some of these other structural isomers. So we'll be doing that next time.